lecture and then do more hacking for the rest of the afternoon. And I understand Jose Miguel talked about Bayesian decision theory a little bit, so I hope this gives a very practical view where he might have given a more philosophical view. I don't know. Either way, maybe it doesn't hurt to see it again. And then I wanted to talk a little bit about source detection, and I'll kind of see how the time's going, and we can decide to skip that or not. Okay? Okay, so I was supposed to talk about working on large surveys and Bayesian statistics. So this is, I think, the part that is most related to that. So my work is all about going from images to catalogs. A lot of astronomers don't really like images. They just want catalogs, right? So I'm one of the people who kind of works at that bottom level so that other people can stand on my shoulders. Yeah? Oh, okay. I'm invisible. Sure. Okay. I'll go stand in the... Where's the... Oh, is it there? Okay. All right. All right. So basically, you know, the goal is to find and measure stars and galaxies in images. So this is traditionally done with estimators or, you know, algorithms or recipes or whatever you want to call them. And I try to bring a bit of a Bayesian flavor to that kind of job. As you've seen, I'm a little bit of a, not as rigorous with my mathematics as, and I'm not a very good Bayesian, but still I try. So here, just to give a little bit of a flavor of like what I'm trying to do in my work, on the left is a little postage stamp of a galaxy. In the middle, a parametric model of that. It's actually just a really simple model that says it's an exponential profile galaxy convolved by the point spread function. And that produces a pixel-by-pixel model of what the image ought to look like. So, you know, in our little example, our model was M and B, or like our model parameters were M and B, and our prediction was just that the Y values are given from MX minus B. Well, here I'm making a prediction for every pixel based on a slightly more complicated formula than that. And then basically just you want to, just like that problem, we're trying to minimize the chi-squared difference between the image that's actually observed and the model prediction of what should be observed. Okay. And that's, so traditional, like more source extractor or something like that would do something different, like say try to measure or compute the second moments of the pixel values or something like that. That's more, doesn't involve an explicit model. Okay, but that's, that has not really probably going to talk very much about that today. So I wanted to talk first about, before we can measure objects in images, we have to detect them. And so I'll probably talk about detecting sources. Sources in my world is just a star or a galaxy. And the big question is, at each pixel, is there a source here? Or at each point in the sky, is there a source here? Now, traditionally, you might think, oh, you just do some operation and apply a 5 sigma cut or something like that. And I'll show you that that's a particular choice, and you can make other choices in a rational way using Bayesian decision theory instead. And this leads to an idea of catalogs or lists of detections that are a little bit more customized to particular goals. So often catalogs are kind of built as a single catalog that's supposed to be good for everybody who wants to use that data set. And I kind of think that a more a more free view is more appropriate, but we'll see. And I guess another theme is the distinction between making hard decisions or propagating uncertainty forward. And you know, as Bayesians, we love propagating uncertainty forward rather than stating just an answer. We want to always give a distribution of possible answers. Okay, so Bayesian decision theory, I think, boils down to first writing down your expected utility, or writing down your utility, and then doing Bayesian computations over those values. So a utility is just, so the setup here is that you have a number of different decisions you can make. So I will go to restaurant A or restaurant B or restaurant C. And there are different outcomes or real states of the world. You know, restaurant A has delicious food. Restaurant B has delicious food. Restaurant C has delicious food. It's Spain, so they all have delicious food, right? So for each of these states, or for each of these combinations of the actual state of the world and the decision you take, there's some outcome and, you know, some goodness of how pleased you are with that outcome. And you can measure that in whatever units you want. Like, that's not really specified by this. So you can think about measuring it in units of deliciousness of your meal, or in euros, or in, you know, something else. Basically, this is a really subjective statement of what you want the outcome to be, or how much you value each outcome. Okay, so I'm going to look at just much simpler examples where we just have two states and two possible actions. But, you know, keep in mind that often the case is there are many different actions and many different states. Now, we want to look at the expected utility of each of those, of the two actions, right? So our choice is we can either take action A or action B. And so I'm kind of abusing the notation a little bit, but I've written down, I'm writing down expectations as a big E, and that thing is the thing we're taking the expectation over. So, you know, basically taking that expectation is just, there are two possible states of the world, and I'm simply multiplying. This is, if we don't have any data at all, all we know is we have a prior over this possible state of the world and a prior over this state of the world. We just sum, weighted sum the two utilities. So this is if you have no data about the situation, then basically you simply rely upon your prior. And if you've, read 9 reviews that say that restaurant B is better, then, and you believe that the outcomes, your utilities would be the same for both, then you're probably going to go to restaurant B. So now okay, that's just the same, right? That was just writing out the expectation. Now, if you actually get some data, then you're getting into the realm of Bayesian statistics. So then we have some probability for this state of the world given our data. Now, plugging in Bayes' rule, you get that part. So now we're looking. So we've got basically the same thing. We're back to having a prior, a likelihood, and then, in my world, a normalizing factor that I don't care about. If you can, right, so that's just the same thing, putting that normalizing factor at the front. And then, so you can sort of rewrite this as a sum over states. This is just writing out these two terms, collecting these two terms as a sum. So there's state alpha, state beta, prior over that state, likelihood on that state, and utility for that state. And you have to compute that for each of, all of this was for action A, and you do the same thing for action B. Right, so it's actually really straightforward. It's like just a really nice little formulation. And then essentially you take action A if that has the best expected utility of all the possible actions. Okay, so, sorry, I don't know why I put so many equations here. It's way too many equations. This doesn't say anything useful. That's just writing out just writing out what the expectations are. So, you know, conveniently enough, the normalizing factors go away, and you end up with this sum over states of prior times likelihood times utility. So, it's really simple and clean. Okay, now I was going to go through a whole thing on betting on a coin flip. I don't know if it's really kind of belaboring the point, but maybe I'll just do it anyway. Okay, so imagine you're in a casino where where the odds are, as they always are in casinos, the odds are a little bit loaded against you. This is a bet on a coin flip. If it comes up the way you bet, you get 9 euros. If it comes up against the way you bet, you lose 10 euros. Right? So that's really how the games usually are set up. They're usually just not written down in that way. And now let's say that that the coin flip is actually fair, or at least you believe it to be fair. So your prior is that heads is equally likely as tails, and you have no information yet. So you have no data, so the likelihoods are nothing, or 1, or something like that, or just the same. Right? So then the two things you can do are bet heads and bet tails. In this case, go home wasn't an option, I guess. You could think that, you know, usually that is an option. You could just, if you're in the casino, you could go home. So, you know, in this case, there's some expected utility. Again, I've taken out the normalizing factor. So these don't actually tell you how much you're likely to lose in euros each time you play the game. It's off by a factor of 2, I guess. But, you know, it tells you that betting heads and betting tails are exactly the same. You're going to lose a little bit each time. So now imagine that you have a little machine or some magical device or something, a camera or Google Glass or something like that, that gives you some weak information about whether it's going to come up heads or tails. Right? That's a little bit of data, and that feeds into the equations. So imagine it tells you that it's a little bit more likely to come up heads than tails. That sways the expectations enough that it tells you to bet heads. Or, you know, imagine you, this is going to be silly, but imagine you have some information that the coin is loaded, the coin is not fair. So that's maybe you might count that as prior information. Yep. So those numbers came out of the air. They came out of, so okay, that's actually really good. Okay, I sort of cheated there. I said, the rules of the casino are this, right? And then I said that I'm going to measure my utility in euros. Right, so I said simply that the outcome in euros is what I'm going to count as my utility. So the numbers didn't. So essentially, you have to make the decision before you know what reality is going to be. So all you have to go on is your state of belief about reality. If that makes any sense. So you know that after the fact, after the coin flip turns out, that then you're simply down to one of the columns. So if it comes up heads, then you read off what happens to you based on which action you took. No, not quite. These aren't betting odds. They're the outcome, like what happens to me in that combination of states. So if I bet heads and heads comes up, then I get €9. And if I bet heads and tails comes up, then I lose €10. Yeah. Yeah. Yes, indeed. Yeah, so it's an arbitrary choice of unit, kind of. Right, exactly. So what people write down for their utility tells you a bit about their psychology. Yes. Right. Yeah, so that's is there a good alternative or like a good way of dealing with that? So, okay, yeah. Yeah, exactly. Well, so that's the thing. It really is, it's effectively a subjective choice. If you want to be rational, you decide to use Bayesian decision theory to make the decision, but then you have to write down your utility matrix, and that's really just a statement about what you want to happen, what your desired outcomes are. So it's really the tricky part of deciding to actually do Bayesian decision theory. And yeah. Yeah. Right. So if there were a go home row in that column, if there were a go home row that just had 0 and 0, that would in fact be the highest utility option, right? Because we saw that the other ones were, if you play the game, you lose, on average, in expected utility. If you go home, you get nothing. Yes, right, exactly. So you could imagine writing another row that has the same rules for the casino, except now instead of betting 10 euros, I bet my entire bank balance. Maybe not that different from 10 euros. But still, but then that might make the problem more interesting, and it would be a way of thinking about Brendan's point, where you might actually have very negative utility for losing everything you own. That might actually be a very bad thing, and where it wouldn't be balanced by the positive utility of doubling your life savings. So in that way, you could think about dealing with that nonlinearity by adding more rows for your options of things to do. Okay, so I'm going to, you raised another good one, which is, what if I just really love betting heads? I mean, it's just something about my makeup that I get, no matter what happens in the game, it just brings me a €2 thrill of joy to bet heads at the casino. Then that also tells me that I should bet heads. And it tells me that I'm going to come out with a positive utility. I'm going to lose euros, but I'm going to gain the joy of betting heads in the casino, along with losing some euros, right? So your subjective utility need not reflect some other person's objective or some other person's subjective utility. My friend might think that a friend who loves betting tails in the casino might think that I'm an absolute fool. And the person who went home thinks we're both fools. Okay, so that's kind of the casino version of Bayesian decision theory. Now we're fine for time. I'm going to do it. Okay, so now I wanted to bring it back to astronomy for a bit and talk about you've got an image and you want to detect stars. Yeah. So if you've decided to use Bayesian decision theory to do this rather than just putting a 5 sigma cut or something, that means the first thing you have to do is write down your utility matrix, right? So I've given us a rather limited set of options, which are to claim that there's a star or to claim that there's no star. And I'm going to do that for every pixel in the image. So I'm going to say, is there a star like centered or near this pixel? And we're going to run that test for every single pixel in the image and say, is there a star here or is there not a star here? Right, so we're going to run this, run this whole decision process like 1,000,000 times for each image. Okay, so the two things you can do are claim that there's a star there or claim that there's no star there. And the truth of the matter can be that there is a star or there isn't. And so these things, have really creative names that are common in science. True, positive, false negative, true, negative, right? So the positive, negative part is whether the thing is actually there or not. No, did I write it down wrong? Oh, no. True, negative. Yeah, okay, I wrote it down right. Hooray. The truths are whether you got it right, and the positives and negatives are whether your claim was that or not. It's going to be just a scalar for each of those, like just a constant for each of those possibilities. Okay, so you could also, so in this example, looking at the image at the bottom, you can, if you sort of squint and are used to looking at kind of dodgy signals, you might count a number of stars. In this one, I made it a little bit more faint, so it's even more challenging. So instead of calling them true positive and false positive and so on, I like to think of them as, hooray, we found a star that's actually there, so we get €1. We missed something that wasn't there, lose €1. Claimed that there was something there and wasn't, minus €1,000. And claimed that there was nothing there when there was nothing there. Not very exciting. This tells you something about my state of mind. But we'll see that that's actually a pretty common view. Yes. Yes, good, excellent. So I think I say in later slides, but I should have said it earlier. If you can avoid making hard decisions, do it. If you can avoid doing this, by all means, definitely do that. If you can convince your collaborators that you should give them a probability distribution, then that is fantastic. However, they usually want catalogs, in my experience. A common counter to that is, what if I give you a sampling of catalogs? Right? If they can run their analysis once, they should be able to run it 50 times on 50 different samplings of catalogs, and then they'll get an ensemble of answers. Then they'll have some statement about the uncertainty in their analysis. I think that's a way forward. Besides, usually in cosmology, you run your analysis 1,000 times or something on mock catalogs or something. So what's wrong with running it 50 times on samplings of the real data? So yeah, if you can avoid doing decision theory, do. It's hard to write down your utility matrices and you feel funny. Okay, so let's go back to filling in the rest of it. The other thing we have to do is something about, is writing down priors. And so I just wrote down numbers for a typical kind of setup where your image is maybe 1,000 by 1,000. And for common like optical images, there might be 1,000 sources in it. So you've got about 1 million pixels and about 1,000 stars. So, per pixel, the prior of having something there is 0.1%. And now the other thing we need is likelihood. I'm going to kind of gloss over that for a moment, and we're going to just assume that all stars are the same brightness. So oh, yeah. Yes. Yeah, indeed it is. Yeah. Yeah, exactly. There's no connection between that number and this. Right. We'll see sort of how it plays out in the decision. So imagine that we're going to look at pixels now, and so on the x-axis here are the pixel values, right? So these are noisy images, so there's some distribution of pixel values where there are no stars, and there's also a distribution of pixel values where there are stars. And so I assumed here that all stars are brightness 6, and the noise in the images is 1, like is Gaussian with standard deviation of 1. So if there's no star, then you have this blue distribution of pixel values that you're likely to see. And if there is a star, there's this distribution around 6. Okay, so then if you plug each of those pixel values in and compute the expected utilities, you get out this, which says, okay, so here are the two claims you can do, right? You can claim that there's no star, or you can claim that there's a star. And then I'm plotting the expected utility as a function of the pixel value, right? So if the pixel is really negative, then you're far better to claim no star than to claim that there's a star there, right? If you read off, if the pixel has value -3, then it's 9 standard deviations from being a star and only 3 standard deviations from being nothing. So, it's sort of, the odds are totally in favor of it, of there being nothing. And then, likewise, if you read off 12 or something, then it's far more likely to be a star of brightness 6 that has noise added that brought it up to 11. Still incredibly unlikely. It's, far more likely to be that than to be 11 standard deviations from 0. Okay? And now there's a funny thing in the middle. It's really hard to make marginal decisions, right? Your expected utility actually dips in the middle there. So that's sort of like the reason to avoid making decisions if you can. And then, so I guess the other thing to say is that when the data are conclusive, your expected utilities sort of converge to your actual utility, or like to the utilities you wrote down. So now, as you, so if you adjusted say you said it's actually much worse to miss a star than I wrote down, then as you increase the cost of missing something, then that sort of shifts this curve down, and it means that, oh yeah, the other thing I forgot to say is you should do the action that has the highest utility. So you should claim no star up until this point, and then you should claim there is a star. So you can see that if you change it so that it costs you to miss something that's actually there, then this moves your decision threshold to lower and lower sigma values. So now it's telling you, instead of detecting something at something like 5 sigma, you should detect at more like 4 sigma. If it costs you almost the same to miss something as to make a false claim, then it pushes your detection threshold lower. Kind of makes sense, right? And I think that's, oh yeah, okay, so now we're fine for time. I was going to say, let's discuss with your neighbor, or maybe we'll just like talk amongst as a group. Say, what would happen if the prior on stars were larger? Right? Like if you just knew that there were more stars, right? What would that do? Anybody want to hazard a guess? If instead of 1 star every 1,000 pixels, there were 1 star every 10 pixels. Intuitively, what does that make you think? If you think a priori 1 out of 10 pixels is going to have a star, it should sort of push you into being more likely to believe that there's a star, more likely to report that there's a star. Right? Okay, here's a good one. What about if instead of all stars being brightness 6, what if there's a luminosity function? As there is, right? As you go fainter, there are more and more things. There's a really steep luminosity function for stars. So you actually know that, I said those marginal decisions are hard. In detecting sources in optical imaging, everything's a marginal decision because all of the majority of the objects are at the decision threshold. So if you know that as you go to lower and lower fluxes, there's going to be more and more stars. And it's even something like log number. Then that means that your prior, as you go to fainter and fainter things, is going to be shooting up. Right? So that's actually should kind of distort change the utility function to push you toward making more marginal decisions, or claiming more stars, because your prior is that there actually are more stars that are really faint. right, and then I'm just gonna, okay, I'm gonna skip past the other ones and just go to the bottom and say, now, what if you had other information and you could measure, say, like the colors or other properties of stars? Like, so instead of just having measuring in a single band, you could take into account more information and say, well, it would be really interesting. Like, it would be, if this thing existed, if this thing is real, it would be pretty interesting. If you detect polarization of the CMB or something, then that's good. So that would let you make decisions that could be perhaps driven by your goals rather than just simple like sigma cuts and catalogs. Anyway, this is my dreaming, I guess. Okay, so I guess if you have to make a hard decision, then Bayesian decision theory is a rational way of doing that, and it involves writing down the subjective part that says what you want to happen, basically. Other than that, you just have distributions and nothing that tells you what is good in the world. But really, at the end of the day, for detecting stars and other things like that, it boils down to a significance threshold, right? Once you've written down your utilities and priors and likelihood, then you get that curve I was showing as where you have the expected utility as a function of flux, and those curves for claiming or not claiming a star cross at some point. And that's your detection threshold. So that tells you if you have this policy or this utility, then that tells you where to set your threshold. And the pretty extreme values that I wrote down, a prior of 0.1% and a utility where you lose 1,000 for making a false claim. Sorry, I'm going to go back, which is a bad thing in talks. No, apparently I'm not going to go back. Oh yeah, okay. So you can see that, those rather extreme values I put in actually lead to a decision threshold that's something like 5 sigma, right? Maybe even less than 5 sigma. I haven't exactly read off what it is. But 5 sigma is pretty extreme. Anyway. Oh, great. Oh, apparently I'm at the end of my talk. Thank you. That is actually a logical place to stop, so let's. So I was thinking that we would just simply spend the rest of the afternoon working on the problem set. Oh yeah, so one opinion is that I think maybe the second last one that says look at the linearly squares uncertainty and compare that to what you got from MCMC. I think I would skip that and move on to outliers because it's more interesting, more relevant. So that's my opinion. Skip that one and move on to outliers. Okay, thanks.